Welcome back to The Explainer. Today we are diving deep into the world of forensic science. A place where every single piece of ash, every little shard of glass has a story to tell. We're going to follow the clues left behind by fire and explosions, and trust me, you'll be amazed at what they can reveal. Right, so imagine this. The sirens finally fade away, the smoke starts to clear, and that's when a completely different kind of expert arrives on the scene. Their job is way more than just looking at the damage. It's about piecing together a really complex chemical puzzle. And you know what? The very first clues are often hidden in plain sight. So, how in the world do they do it? How do investigators literally read a story that's been written in fire and ash? Well, we're about to find out. We're going to follow the evidence from the chaotic crime scene all the way to the sterile lab, and you'll see how the tiniest, almost invisible traces can lead to the biggest breakthroughs. Okay, so to really get a grip on the investigation, first we have to understand the event itself. At the very heart of both fires and explosions is this powerful chemical reaction. But it's the small, subtle differences in this reaction that change absolutely everything. So at its core, it's a pretty simple definition for a really powerful process. Whether it's the slow, steady burn of a log in a fireplace or the instantaneous, violent blast of dynamite, it's all about fuel and oxygen combining to release energy. But, and this is the key part, the devil is really in the details. And this is where it gets really fascinating. A fire is slow, right? That's because it has to literally pull oxygen from the air around it to keep going. But with explosives, they bring their own oxygen to the party. For low explosives, it's physically mixed right in with the fuel. And for high explosives, it's actually part of the molecule itself. That's what allows for that incredibly fast supersonic reaction that creates such a devastating shockwave. Okay, so with that little bit of science under our belts, let's join the investigators at the scene. Amidst all the chaos and destruction, they have one primary goal that's going to guide their entire search. A single point that holds the key to the whole investigation. This is ground zero. For a fire, they call it the point of origin, where the very first flames ignited. For an explosion, it's the bomb seed, the epicenter of the blast. This spot is absolutely critical because it's where the most concentrated evidence is most likely to be found. Things like trace amounts of accelerants or tiny fragments of a device. Finding it isn't just about the chemistry either. It can also be the key to finding physical evidence like fingerprints or even DNA. And finding that point of origin is all part of a very methodical process. They don't just rush in. First, they have to secure the scene, to protect the evidence from contamination. Then, the hunt for ground zero begins. Every single observation is meticulously documented with photos and notes before, and only then can the crucial work of collecting that physical evidence start. Now, let's put ourselves in their shoes for a second. Imagine you're an investigator and you've just found some really promising debris at the point of origin. The next challenge is just as critical. How do you get it to the lab without losing the very chemicals you're trying to find? It's not as simple as just scooping it all up. While investigators do use special evidence bags for some things, in arson cases, they often turn to something that's surprisingly low-tech. Just simple, airtight metal cans. Yeah, they might look like paint cans from the hardware store, but they serve a critical forensic purpose. So why the can? Why not a plastic bag? Well, it all comes down to a property called volatility. Think about the smell of gasoline when you're at the pump. Those are the chemical vapors, right? Well, if an arsonist used a liquid accelerant, those exact same vapors can easily escape right through a normal plastic bag. An airtight metal can, though, traps those vapors, making sure that faint chemical signature makes it all the way to the lab for analysis. Okay, so once those cans arrive safely at the lab, the next phase of the investigation begins. This is where the real magic happens, where technology and human expertise come together to identify those invisible clues that are locked inside the debris. And before any of those high-tech machines get turned on, a trained examiner gets to work. With a super keen eye, they carefully sift through all the evidence, and they're looking for anything that seems out of the ordinary. Little fragments of a timer, a battery, bits of wire, or even unconsumed explosive material. For example, just the size and shape of metal fragments can tell them a lot about the force of the blast and maybe even the type of device used. So, to identify any chemical residues, scientists use this really smart two-pronged approach. They start with what are called presumptive tests, which are basically quick screenings to see if any suspicious compounds are present at all.
If they get a positive hit, then they move on to the confirmatory tests to know for sure. And this two-tiered system is incredibly efficient. Think of it like this. Presumptive tests, like a simple color spot test, are fast and can sometimes even be done right at the scene. They give investigators an early clue about what they might be dealing with. But the real proof, the smoking gun, comes from the heavy machinery back in the lab, those confirmatory techniques like gas chromatography that can pinpoint the exact chemical compound with absolute certainty. So how does a technique like gas chromatography actually work? Well, the slide says to think of it as a racetrack for molecules, and that is a perfect analogy. Imagine a sample of the evidence is turned into vapor and injected into this long, coiled tube. The different molecules all start racing through it, but they don't all run at the same speed. Lighter molecules zip ahead, while heavier ones, or ones that stick to the inside of the tube, lag behind. By timing exactly how long it takes for each molecule to cross the finish line, scientists can identify it. It's pretty amazing. So after all that screening, all that separating, and all that analyzing, the entire forensic process, it all boils down to one final make-or-break moment. So here's the crucial point. The data signature, or the fingerprint from the unknown sample, that's the debris from the crime scene, is compared directly to the signature from a known reference material, like a sample of a commercial explosive. If those two signatures, those two graphs, match perfectly, bam, they've got their identification. It is the forensic equivalent of a perfect fingerprint match. And that right there is the real power of this whole process. It takes a scene of just utter chaos and destruction, and step by meticulous step, it applies scientific principles to pull out an objective, factual conclusion. It's about turning confusing questions into solid answers, one piece of evidence at a time. But this all brings us to a final, pretty thought-provoking question. The lab can identify the accelerant. It can tell us what happened and how it happened. But that ultimate question of why, the motive behind the act, well, that's a story that science alone can never fully tell. We hope this journey through the world of forensic science has given you a whole new appreciation for the incredible, meticulous work that goes into investigating these scenes. It's a truly fascinating blend of old-school detective work and really cutting-edge science. Thanks again for hanging out with us. If you enjoyed this, you know what to do, so you don't miss our next deep dive. We'll see you in the next explainer.